Section: Introduction. In this section, we discuss embedding models, which are essential for converting inputs into dense vector representations that capture semantic information across different areas. Text embedding models represent words and sentences as vectors, placing similar texts close together in the embedding space. Recent studies have aimed to create general-purpose embedding models that perform well in various tasks like information retrieval, clustering, and classification. Large language models, LLMs, have shown promise in building these models due to their extensive pre-training knowledge, which can enhance performance across many applications. We highlight two main approaches that have transformed the development of high-quality embedding models using LLMs. First, LLMs help improve training datasets by generating better examples through techniques like hard negative mining and synthetic data generation. This process allows us to distill LLM knowledge into smaller, more efficient embedding models, resulting in significant performance improvements. Second, since embedding model parameters are often initialized from language models, researchers have started using LLM parameters directly for initialization. Although this method requires more computational resources than traditional models, evidence shows that it can lead to much better performance. In our work, we present Gemini Embedding, a new embedding model initialized from the powerful Gemini large language model. We utilize Gemini's capabilities to train Gemini Embedding on a wide range of embedding tasks. To create a high-quality and diverse training dataset, we use Gemini for important data curation steps, such as filtering out low-quality examples and generating rich synthetic datasets. This curated dataset allows us to train with a contrastive learning objective, helping Gemini Embedding learn strong semantic representations. Building on the success of our previous model, Gecko, we add task prompts and a pre-fine-tuning stage to boost performance. We also apply model soup, a straightforward parameter averaging technique, to combine multiple fine-tuned checkpoints, resulting in a superior final embedding model. To thoroughly evaluate Gemini Embedding's capabilities, we conduct extensive tests across various tasks and languages, primarily using the Massive Multilingual Text Embedding Benchmark, MMTEB. This benchmark includes over 100 embedding evaluation tasks in more than 250 languages. Notably, Gemini Embedding achieves state-of-the-art performance on the MTEB, significantly outperforming previous models. It ranks first on the public leaderboard based on Borda rank and achieves a mean score of 68.32, which is a notable improvement over the second-best model. Additionally, it shows exceptional performance in both high-resource languages like English and low-resource languages such as Macedonian. We provide a detailed ablation study to clarify the key factors that contribute to Gemini Embedding's outstanding performance. In the related work section, we note that text embeddings are crucial for various natural language processing tasks, including semantic similarity and information retrieval. Previous models like Universal Sentence Encoder and Sentence T5 aim to provide general-purpose embeddings but face challenges in generalizing across different tasks. This has led to the development of benchmarks like MTEB, which focus on task and domain generalization. We also discuss how synthetic query generation has been effective in creating diverse training data for embedding models. Some studies have shown that the initial passage used to generate synthetic queries may not always be the best positive example, prompting the use of LLMs to identify better positive and negative passages. Furthermore, LLMs have been utilized as backbones for embedding models, with pre-trained models like BERT and T5 being popular choices. Recent models initialized from LLMs have demonstrated significant performance improvements, although they often require extensive in-domain training datasets, which can lead to overfitting. Section Summary. In this section, we discuss the significance of embedding models in capturing semantic information and highlight the advancements made through large language models, LLMs, for creating general-purpose embeddings. We introduce Gemini Embedding, a novel model that leverages LLMs for data curation and initialization, achieving state-of-the-art performance across various tasks and languages, particularly excelling in both high-resource and low-resource contexts. Section: Gemini Embedding. In this section, we provide technical details about the Gemini embedding model, focusing on its architecture, training objective, and training process. For the model architecture, we designed the Gemini embedding to create comprehensive representations for various tasks like retrieval, clustering, classification, and ranking, utilizing the capabilities of Gemini. We start with the Gemini model and refine it further, which we consider a form of pre-training. When we process an input sequence of 6 tokens, we use a transformer with bidirectional attention, initialized from Gemini, to produce token embeddings. To create a single embedding that captures all the input information, we apply mean pooling, which averages the token embeddings. Finally, we use a randomly initialized linear projection to adjust the embedding to the desired output dimension. Regarding the training objective, we trained the Gemini embedding model using a noise contrastive estimation (NCE) loss with in-batch negatives. Each training example consists of a query, a positive target, and optionally a hard negative target, along with a task string that describes the task type. We embed the query and passages as vectors, and the loss is calculated based on cosine similarity. We do not include same tower negatives in the loss, as this tends to reduce performance. To accommodate different embedding dimensions, we adapted the loss into separate losses across overlapping subdimensions. For our training recipe, we start by initializing the embedding model from Gemini parameters, which we view as a pre-training step. We then implement a 2-stage training pipeline. In the pre-fine-tuning stage, we train the model on a large set of potentially noisy query, target, pairs, excluding the hard negative term from the loss. We find that using a large batch size helps stabilize the gradients and adapt the model from autoregressive generation to encoding. This stage lasts longer due to the larger dataset. In the fine-tuning stage, we focus on a mix of task-specific datasets that include query, target, hard negative target, triples. Here, we use smaller batch sizes and limit each batch to a single dataset to enhance the signal from positive targets. We also conduct a grid search for various training hyperparameters to identify the best checkpoints. To improve generalization, we average the parameters from individual fine-tuning runs. We experimented with different combinations, including averaging from the same or different training runs, and used a mix of data variation and manual selection to finalize our checkpoints. Section Summary. In this section, we detail the Gemini embedding model, which utilizes a transformer architecture initialized from Gemini to create comprehensive input representations for various tasks, employing mean pooling and a noise contrastive estimation loss for training. We also describe our 2-stage training process, consisting of pre-fine-tuning on noisy data followed by task-specific fine-tuning, and our approach to enhancing generalization through parameter averaging from multiple fine-tuning runs. Section: Datasets. In this section, we describe our training data, which includes a mix of multilingual embedding tasks and code retrieval tasks. We utilize Gemini in 3 key ways to enhance our data quality: generating synthetic data, filtering data, and mining hard negatives. For pre-fine-tuning, our goal is to expose our Gemini embedding models to a wide variety of training datasets. We use a large web corpus, focusing on pairs of titles and passages as positive examples. This straightforward approach has proven effective, even when starting from a large language model. During fine-tuning, we create 3 different mixtures to ensure diversity in tasks, languages, and coding abilities. We incorporate a selection of academic datasets from Gecko and several synthetic datasets, while avoiding many in-domain datasets that could introduce bias. We determine the training mixture rates through a detailed grid search based on optimal training steps for each dataset. To enhance our training mixture, we generate synthetic datasets for retrieval and classification tasks. For retrieval, we build on our previous work by using Gemini to create synthetic queries for web passages and filter out lower quality examples. For classification, we produce synthetic datasets for counterfactuals, sentiment, and reviews in English, employing multi-stage prompting strategies to improve quality. Our training data also includes human annotated datasets, but we found that many retrieval datasets had quality issues. We use Gemini to filter out these poor examples based on our quality assessment prompts. In terms of hard negative mining, we identify targets that are similar to true positives but do not answer the query. We first train a Gemini initialized model without hard negatives, then retrieve the top 25 nearest neighbors for each query. We score these neighbors using Gemini and apply two prompting strategies, ultimately finding that the lowest scoring neighbors make the best hard negatives. For evaluation, we assess Gemini embedding across a wide range of tasks, domains, and languages using benchmarks from MMTEB and cross-lingual evaluations like Extreme-Up and XOR Retrieve. MMTEB includes over 250 languages and 10 task types, with our evaluations covering 164 individual tasks. Overall, we present Gemini Embedding's performance alongside other leading models in various evaluations. Our model achieves state-of-the-art results, particularly on the MTEB, multilingual, leaderboard, with significant performance advantages across multiple metrics. Gemini Embedding ranks number 1 in MTEB, multilingual, MTEB, Eng, V2, and MTEB, code, while also excelling in cross-lingual retrieval tasks, setting a new standard for general-purpose embeddings. Section Summary. In this section, we describe our training data mixture, which includes diverse multilingual embedding and code retrieval tasks, enhanced by Gemini through synthetic data generation, data filtering, and hard negative mining. We detail our pre-fine-tuning and fine-tuning processes, the creation of synthetic datasets, and the evaluation of Gemini embedding, which achieves state-of-the-art performance across multiple benchmarks, including MTEB, multilingual, and cross-lingual tasks. Section: MTEB, Multilingual, Leaderboard. In this section, we compare Gemini embedding with leading models from the MTEB, Multilingual, Leaderboard. In our analysis, we find that Gemini embedding achieves the highest border rank and performs exceptionally well across various tasks, particularly in classification, clustering, and retrieval, where it surpasses the second-best model by notable margins. Next, we look at the MTEB, Eng, V2, leaderboard, where Gemini embedding again secures the top border rank and shows impressive performance improvements in classification, clustering, and retrieval compared to the runner-up. For the MTEB, code, leaderboard, we evaluate 8 tasks, excluding 4 additional tasks. Only a few models, including Gemini embedding and Google's Gecko, are evaluated across all tasks. Here, Gemini embedding once more achieves the highest border rank and average performance. We also report the average performance excluding one specific task, and Gemini still leads in this category. We then present the performance of Gemini embedding alongside other top multilingual models on the Extreme-Up cross-lingual retrieval task, which involves mapping queries from 20 underrepresented languages to English. Our results show significant improvements in cross-lingual retrieval capabilities. In our qualitative examples, we illustrate Gemini embedding's effectiveness in retrieving relevant English passages from queries in Assamese and Hindi, demonstrating its strong multilingual and cross-lingual abilities. To understand how Gemini embedding performs well across various tasks and languages, we conduct an ablation study. We show that our model generalizes effectively across different languages and tasks. We observe that pre-fine-tuning significantly enhances performance, and even training on an English-only dataset yields strong results on multilingual evaluations. This indicates that Gemini can generalize well, even with limited language training. However, we note that having a diverse set of tasks is more beneficial for fine-tuning than just focusing on multiple languages. We also discuss our multi-stage prompting strategy for generating diverse synthetic classification datasets. These zero-shot datasets, created without using actual examples, significantly boost performance across all datasets, matching in domain dataset performance and potentially reducing bias. Lastly, we utilize Gemini to filter retrieval datasets, specifically testing the MIRACL training datasets in 18 languages. Our results show that filtering consistently leads to better outcomes across languages, with only minor drops in some cases. This further supports the effectiveness of our English mixture in enhancing quality on multilingual tasks. Section Summary. In this section, we present the performance of Gemini embedding across various MTEB leaderboards, where it consistently achieves the highest Borda rank and excels in tasks like classification, clustering, and retrieval. We also demonstrate its strong generalization capabilities across languages and tasks, the effectiveness of our synthetic data generation strategy, and the benefits of data filtering for improved performance in multilingual contexts. Section: Hard Negative Mining. In this section, we examine the effectiveness of the hard negatives chosen by Gemini. As shown in our findings, using hard negatives generally improves our model's retrieval performance across 4 datasets. However, we noticed that too many hard negatives can lead to overfitting, which negatively impacts retrieval tasks. In our future work, we plan to investigate regularization techniques and better methods for selecting hard negatives to mitigate overfitting. Looking ahead, we aim to expand our embedding capabilities beyond text to include other modalities such as images, videos, and audio. We want to utilize Gemini's strong multimodal features to create a comprehensive embedding model that can represent various combinations of modalities in a unified space. This will involve curating multimodal data tasks that help us learn generalizable representations. Additionally, we will explore training strategies that ensure our model performs well across both single and multiple modalities.